I'm going to go over the goals a little briefly with you this morning. Essentially, what we planned for this 2-day workshop, since it is only 2 days, what we would like to do is to give you guys some experience, allowing us to demonstrate to you how we come up with method parameters for analytes. And we're going to do that by infusing some drugs on the instrument. We're also going to show you what we have determined for our purposes is system suitability, including tuning parameters that we have set up in our laboratory and a standard mixture that we inject to make sure the entire system is working properly before we analyze samples on it. We're also going to give you guys experience doing unknown sample processing. That's going to include single analyte compounds and a multi-analyte mixture so that you can see that even overlapping compounds are easily identifiable with the method. We're also going to give you a brief run-through of the quantitative capabilities of the software, but that'll be very brief. And the very last thing we're going to do tomorrow afternoon is make sure you guys get plenty of personal one-on-one experience with the software and processing so you can become familiar with it. The reason we're interested in doing all of those things is so that you can have some hands-on experience and knowledge to determine if this technology would work well in your laboratory. So the setup next door, when we get over there this afternoon, we're going to be very fluid and very flexible in how we do this, even though it is being recorded, so we can readjust whatever we need to. It's all about you guys learning and getting some hands-on experience. So we'll try some things. If it doesn't work, we'll try some other things. So a little background about myself. I have worked at the GBI for, it'll be 9 years this November. Mike has been there 2 weeks longer than me. So we originally knew each other from graduate school, so we've known each other even longer than we've worked at the GBI. Most of my experience is with postmortem samples, and most of Mike's experience is with drugs of abuse in traffic samples. So with the two of us, you're actually going to get both ends of the toxicology spectrum, which I think will be nice.
Okay, so a little bit about where my experience with MS before we get started. Basically 4 years ago, I couldn't imagine anything really much more than GCMS in perpetuity for doing tox work. And then we got this grant to bring it into the laboratory. And so the way these talks are arranged, it's kind of like you've uncrated your very expensive piece of equipment, and now what to do with it. And so they're going to seem, they may seem a little basic, but you know, 4 years ago, I really knew nothing except for that it was very expensive. It cost more than I do for a couple of years. So it must be important, right? And almost all my LC experience has been with our Applied Biosystems Q-Trap and then 3200 Q-Trap. Some of the parameters and things in here are going to be very specific for that instrument, but I suspect other instruments, you know, they'll translate in some way. So, and a lot of the things are sort of standard throughout the literature. But without further ado, I'm going to get started. So I'm going to cover sort of what are the advantages of LCMS and MS or 10MS spec over gas chromatography, mass spectrometry. I'm going to talk a little bit about the importance of chromatography. A lot of people get caught up in the MS and sort of forget that chromatography can be important, and it really can be, especially when you consider some of the drawbacks of the ionization method. We're going to talk about API, atmospheric pressure ionization. But we're going to focus on electrospray. That's the one we've applied in our laboratory. That's the one we have all the experience with, and it really works well for most drugs. Small molecules is what they will call it. So most drugs are covered by electrospray pretty well. We're going to focus on tandem mass spectrometry, really, especially triple quadrupole orientation rather than ion trapping. But we are going to talk about the hybrid capability, the sort of linear ion trap that the 3200 has available to us. We're going to talk a little bit about MS modes of analysis, but we're going to focus on two, which is MRM, multiple reaction monitoring, and product ion scanning. There are many other experiments that are available to you, but these are the two that we have applied to qualitative screening of unknown samples. And then I'm going to talk a little bit about the Q-trap parameters themselves. So I'm going to start using the terminology that really relates to the 3200 Q-trap. which is the instrument that you'll be working on for the 2 days that you're here. So why should we buy a $250,000 or $200,000 piece of LCMS MS equipment? What advantages does it bring to you over GCMS? Well, if you've done a lot of GCMS work, you know you have to do a lot of derivatizations to get to metabolites or anything that's polar, and you spend a lot of your time cleaning up the blood specimen and then derivatizing the drugs so that you can actually just get them through the GCMS. LCMS and liquid chromatography really allows you to not spend nearly as much time cleaning up the specimen, and you don't have to do nearly as much, or if any, derivatization on a lot of different compounds. You may have to do for some special analysis, but a lot of things that we used to derivatize routinely, we don't have to derivatize anymore. We just run them right through the instrument. These compounds, since even though you're going to see temperatures of like 500, thermal stability is not really an issue unless you make it really hot or the compound is very sensitive. And with electrospray, it really is drugs will not fall apart very well unless, like I said, they're very sensitive. MS, MS gives you additional structural elucidation. And what it really does, especially for product dyne scanning, it allows you to isolate a compound and then fragment only that compound. And that allows you to isolate and then get all this wonderful structural information which you can use for great automated library searching so that you can identify your particular compound for more than maybe just an MRM transition, which is what we'll talk about a lot. Because you can isolate a compound, unlike an LCMS where basically, just like GCMS, whatever comes off the column is what gets ionized and then fragmented right there in the source, and you analyze that. For LCMS, I can have multiple overlapping compounds and I can pick them out. And as long as they have different masses, I can separate one from the other. There are some more useful MS modes if you're interested in exploring a drug, breaking it apart and finding out what it is. You can use some of the MS modes. You can break it apart, or you can look for losses of particular ions. So if you have something that's really unknown, you want to know what it is, MS allows you to do those experiments in a way that single quadrupole MS cannot. We're not going to really cover most of those modes because what we really want to know is what's in that blood specimen. So the system configuration is a bunch of rectangles here. Liquid chromatography is kind of grayed out. It's very important. There are a lot of different columns. There are a lot of different solvent systems. The two that I've seen dominate the literature are acetonitrile and water and methanol and water with a matrix modifier of some sort. Ionization, electrospray, APCI is atmospheric pressure chemical ionization. There's also atmospheric pressure photoionization. We're going to focus primarily on electrospray. Triple quadrupoles, ion traps, and hybrid instruments are all available. We're going to talk about, by the end of the talk, we're going to talk about a hybrid instrument, which is the 3200 Q trap. But it is in the triple quadrupole formation. In other words, there are 3 quadrupoles lined up, and that's what we're primarily going to talk about. All right, atmospheric pressure ionization. It really did revolutionize LCMS. It really made it available to everybody. It made it easy to get your compounds out of this liquid phase and into the gas phase and into the mass spectrometer in a way that everyone could access. It's very increased sensitivity, and all of a sudden you started to see a lot of forensic applications in the laboratory. Its sole purpose is the desolvation and or ionization of analytes, and that occurs at atmospheric pressure. There's actually a chamber. It's filled with, pure nitrogen or something, or even air. It's just, it really is kind of weird. You just think, well, mass spec's got to be high vacuum. Well, there's a chamber where there's a spray, and it sprays, and somehow magically through the process of electrosprays, we'll get to know, that spray generates a little gas phase ion, and somehow only that ion gets sucked into the mass spectrometer in a way that we can analyze. The gas phase ions are sampled directly into the high vacuum system. Basically, any residual gas gets pumped away, and your ion ends up being fragmented later on. Like I said earlier, there are several common modes that really differ by the ion formation. Electrospray is the one we're going to talk about, so I'll sort of skip through that one. Atmospheric pressure chemical ionization, essentially you have your LC column exits, the liquid is sort of volatilized in a heated chamber, a nebulizing chamber. And then a corona discharge needle implies a lot of charge to an area where the LC mobile phase is there. It transfers that charge to the mobile phase, which then transfers the charge to the ion itself. Then now you have an ion formed in gas phase, and it sort of flows out and gets sampled in by the mass spectrometer. Phonoionization, instead of that corona discharge needle, there's just a high energy UV lamp. And there are some new dual sources that do both at the same time. So the question you might be asking yourself is, which of those ionization methods is the best one for me? And it really depends on your application. The more polar your compound and the higher its molecular weight and the more thermally unstable it is, it's going to favor electrospray. However, most of the drugs that I deal with on a daily basis are pretty polar. I can pop a proton or take a proton off pretty easily. And so these are easily analyzed by electrospray. If I have a protein that I want to analyze, electrospray is my way to go. If I have lower polarity, lower molecular weight, these things tend to favor APCI or APPI. I've seen drugs of abuse done by APCI routinely, so that's an easy way to go within your laboratory. I think steroids tend to prefer APCI. It really depends on what works best for you in your lab and what you're the most comfortable with. I will tell you the electrospray tends to dominate the literature, especially the older literature. There's a lot more APCI type applications out there now. So, okay, so yes?
Are there cost restrictions? Why wouldn't you just get a dual source? Are they that much more expensive?
The source that we have, I can't go back. The source that we have on the 3200 actually switches on the, it's like 5 minutes of work. I don't know about the dual sources. They may be, I'm sure they cost more. But the 3200, the original Q-trap we had to change between them, you actually had to pull the housing off and put a new housing on. But the newer ones, it really is just a new tube. It takes 5 minutes.
So you can do either or, but you can't do both. Whereas the simultaneous one or the dual source, you could do it kind of on the fly on the same injection.
Yes, yes, and that would seem to give you access to more different types of compounds at the same time. And one might be much more sensitive in one mode versus the other. So, electrospray. I've talked about it already. Electrospray is simply a method of getting the solution phase ions into the gas phase so they can be sampled by the mass spectrometer. The key phrase here is getting the solution phase ions. Usually in electrospray, you've added a matrix modifier, and so your ions are already there. They're already floating around in the solution. What you're trying to do is get them out of the liquid and into the gas, and then from the gas into the mass spectrometer. The three fundamental processes associated with electrospray are the production of charged droplets, droplet size reduction and fission, and then gas phase ion formation. Each one of these things can be tweaked a little bit in your method setup. And I'm hoping by the time we get all the way to the end of this, you'll see how you can tweak each one of those in the source. Because really, about half the battle in this thing is getting your ions out of the liquid into the mass spectrometer. And then you can do all kinds of fancy collision experiments with those. So the first of these processes could be looked at, well, I guess we'll talk about sort of an overview. This is for sort of the geometry of our older source. The new 3200 sources are perpendicular. The opening, the orifice hole is perpendicular to the sprayer. And that's really great because that means you don't have to clean the plate nearly as often. And it also means that if you're like me, the first thing I do is spray the thing right at the hole, and so then I have to vent it and clean everything out. So if you've heard me say before, I've learned a lot about LC by breaking it repeatedly, really at the worst possible times. This part here is the sprayer tip. The sprayer tip is a metal capillary into which your LC effluent flows. And around that tip is a coaxial flow of gas. That's the nebulizing gas. And then the whole thing is inside a housing. When you look at it, when you actually look at the source later on today, what you're probably going to see is the housing. And when you get in there and squint, you're going to see the capillaries just sticking out of the end of it. between the end of that capillary and the curtain plate, which is right here, the curtain plate, there is a potential. It depends on your experiment, but we typically set it at 5,500 volts for positive mode electrospray ionization. So the next major process, so the first part up there at the top where the nebulizer tip is, that's where your gas phase, that's where your droplets are formed. The second part is droplet solvation or desolvation and fission. This is often assisted by what you can see here, the little red squiggly arrows. That's the drying gas that gets applied. And the last step here is where my gas phase ion is finally generated right before we get to the plate, and it gets sucked in to the mass spectrometer this way, but it has to get through sort of a flow of curtain gas coming the other way. So those are the sort of 3 steps. So 1, droplet size, droplet formation; 2, desolvation and fission; and 3, gas phase ion formation.
What curtain gases are typically used in our environment?
I think in here it's nitrogen. I believe that's what we're using. I think that the drier and more pure the air you can get, or gas you can get, the less any gunk that could get into the Q0. So you want a clean, pure gas at that point.
There's no unique gas delivery issues that came with your LCMS and
As far as we have a gas generator that generates both air and nitrogen. I believe the nitrogen is plumbed to the curtain or the collision cell and to the curtain gas, and the coaxial flow and the drying gas may actually be 0 grade air. All right. So the first process here is droplet size or production of charged droplets. Again, that large voltage of we use 5,500 volts is applied between the end of a capillary carrying the LC mobile phase and the mass spectrometer entrance. Ions of the same polarity. For the rest of this talk, I'm going to talk about positive mode. So we're talking about positively charged ions. So typically in electrospray, that's M plus H. Ions of the same polarity are drawn out towards the counter electrode, which is the curtain plate, pulling the mobile phase along. So if you remember from this previous slide, it's not a mistake that I have this big, I have to remember to press my button, this big thing right here. That structure is actually called something called a Taylor cone. And if you didn't have any LC flow at all, you put that potential in there, the ions in the solution, remember the ions are already there, will actually start pulling the liquid with them. And they'll form a structure, and it'll get longer and longer and longer until all of a sudden the surface tension is overcome and a droplet forms. Like at the end, when the excess charge of the tip of the capillary overcomes the surface tension, a droplet is formed. So they're getting pulled out, and poof, you get a droplet. And that droplet is enriched in those positive ions, hopefully your analyte. And that droplet then begins to move towards the curtain plate, which is the opening of the mass spectrometer. Yes?
This is a positive mode. If you're running it in a negative mode, would the surface charges be negative?
Yes, they would. In negative mode, the M minus H's would be the one trying to get to the curtain plate.
Okay, I meant the charges on the droplet rather than the ion itself.
I think the droplet. I think the droplet itself is being carried. The fluid is being carried along by the charged droplets, by the charged ions inside. So I always think of a positively charged ion that has a sort of hydration sphere or whatever around it. It's carrying things with it. In positive mode, this droplet is enriched in positive ions, and there are going to be some negative ions in there, but mostly they're enriched in positive ions. And in negative mode, it's just exactly the opposite. It's going to be enriched in negatively charged ions, and it's going to be drawing the liquid with it. Does that make sense?
You talked about acetylnitrile and methanol before as your organic side. Which side do you have any aqueous mode? What's the normal buffers you're working with for aqueous point of LC?
We use methanol and water are the two. A is water. B is methanol. Both are modified with formic acid and ammonium formate. Acetic, I think, acetates are also a matrix modifier for the production of ions in the solution. There are many more depending on your application. I think ammonium formate is particularly useful as it's volatile and can be easily removed. Any questions about how we're getting a droplet out there? Basically, we're hitting it with a 5,000 volt charge, and it's those ions cannot wait to get to the curtain plate because they want to be there. Of interest here, what happens is the actual capillaries where the 5,000. That's plus 5,000. The actual curtain plate is at ground, so it sees the difference, and it just I want to be there. The second thing here is droplet size reduction and fission. This is where I'll get to use one of my favorite terms in science. Droplet size reduction occurs by the continuous repetition of two processes: desolvation, which is the evaporation of the neutral solvent in volatile buffers, and droplet fission caused by the electric repulsion between like charges. So, you saw in my original graph there was a little red squiggly lines. Those are there because, unfortunately, I like to have an LC mobile phase. So I have lots of fluid coming in, 200 microliters a minute. Doesn't sound like a lot, but for electrospray, that's a lot. And I end up with these big droplets. I think they're about a micrometer in size. And I got to start shrinking them. And the way I start shrinking them is I start applying a heated gas to that. So they get smaller and smaller and smaller and smaller. And volatile mobile phases and volatile buffers facilitate that because, well, they're volatile and they like to go right to gas and get sucked out into the exhaust. So I want you to imagine my droplet with all these charged ions, and it's getting smaller and smaller and smaller. And all of a sudden, the individual ions are starting to sense each other, and they're getting crowded together on the surface. And something's got to give. And what gives is the expulsion or fission, or if my favorite term, Coulombic explosion occurs. What happens is those little positive charges get expelled. And they get expelled into very tiny droplets, which then shrink and shrink and shrink, and expel charge, and shrink and shrink and shrink, and expel charge. And that process happens over and over in that little teeny space between the end of the capillary tip and the open end of the curtain plate. And you can see here, this is from Nature. These are actually droplets of, I think they're suspended in ethylene glycol or something like that. And I hope you can really see that this is my droplet here. It's been getting smaller and smaller, and now all of a sudden, all those charges are getting crammed together, and it actually elongates in this little football shape and squirts out these jets right here. And those are called Rayleigh jets because the droplet has reached what's called the Rayleigh limit. And the Rayleigh limit is when the Coulombic repulsion equals the surface tension of the droplet. Okay? And they squirt out these little teeny droplets, and you can see them down here. And each one of these droplets is near its own Rayleigh limit. In other words, they're almost already ready to do this process all over again. In fact, what happens is about, I think it's like 90% of the charge gets expelled, but only about 10% of the mass of the droplet. So you can imagine at this first step, I have this big droplet, it hits its near its Rayleigh limit, it expels charge. Now I've got a bunch of really, really small droplets that are all really wanting to get rid of their ions, which is great because that means those ions are going to pop into the gas phase really easily, and that means we'll get increased sensitivity. And that gets me to the third thing. So now I've got probably very small nanometer-sized droplets, and now I'm ready to form an ion in the gas phase. And this is where the rubber hits the road, almost literally. There are several models for bare ion formation. They all seem to play a role. The first one is sort of the charge residue model. This is the oldest model. It says I have a really small droplet. The droplet's so small it only contains one ion, and the volatile mobile phase just evaporates, and I'm left with an ion. The second model is called ion evaporation. It says, look, if I make the droplet real small, all the ions are most likely residing on the surface because on the surface they can be closest to the counter electrode. So and it's also the way they can get the furthest apart. All my ions are residing on the surface, and all they need is just a bump of energy, and they pop right out of the surface and into the gas phase. And this makes the droplet itself more stable because remember the charges don't like to be next to each other. So by getting rid of one little gas phase ion, my droplet gets more stable until it shrinks a little bit more, and then it pops another one off and shrinks a little bit more and pops another one off. And that's called the ion evaporation model. And the last model here is called ion emission. It just says, look, I've got a 5,500 volt potential. Some ions are going to come right out of the source. They're not going to take any droplet with them at all. They're just going to come screaming right out of the source and go right to the plate. The fact is, all three of these models explain some feature of electrospray. The charge residue model really is best applied or thought about for very large molecules. So if I have a protein that's already very large, at some point it's just barely going to have some liquid hanging onto it or water hanging onto it, and it's going to lose the water and be left with a with just the gas phase ion. The ion emission model was elucidated by basically taking very, very, very non-volatile mobile phases, and you still observed ions at the curtain plate. So it can't be happening through desolvation because there's nothing to desolvate. So ions are actually still being formed at the source themselves. Ion evaporation is probably the mechanism that best explains drugs of abuse getting from the liquid phase into the mass spectrometer. A little word about the types of ions that are formed. Electrospray can operate in either positive or negative mode, depends on your application. In positive mode is best suited to basic drugs that form stable HCl salt. So if you buy something from the Fisher catalog or the Sigma catalog that says chloride salt, hydrochloride salt, you're going to be able to do it in positive mode electrospray. Typically, N plus H is the ion that is formed. So if you're like me and you're used to seeing cocaine as 303, I'm looking for my 303, then my 182 and 82 for cocaine. I've had to really think, oh, it's not 303, it's 304. Looking for 304 now. 304 is the one I want to see. So everything is +1. You can also form multiply charged species N plus NH. That's really great if you want to analyze something that weighs 10,000 Daltons or more. You know, a quadrupole probably isn't going to be that great for analyzing something that's that massive unless you can put a lot of charges on it and get its M over Z way down. And that's why electrospray is great for analyzing things like proteins. As a forensic toxicologist, the only thing I care about a protein is getting it out of the way so that I can get to the drug. You will also observe N plus cation formation in there as well. So you want to try to minimize the amount of salts and things you put in there if you can. In negative mode, best suited to acidic drugs that form stable sodium salts. So if you can buy it from Sigma Aldrich and it says sodium whatever, you're probably going to do better off by negative mode. And the primary ion form here is the abstraction of protons, or M minus H. I will tell you that what polarity you use really, again, is whatever works best for you. I've seen, for instance, carboxy THC, which is an acidic, got the little acidic carboxy group on there. Yeah, I've seen it done by positive and negative mode. I've seen it done by electrospray and APCI. Whatever works best for you in your lab is probably the way to go. It's just, you got to know which number to look for. So, we've talked a little bit about electrospray. We know that the whole game here is getting my ion out of the mobile phase and into the gas phase. And some of the practical things that will increase ionization efficiency, electrospray really likes a lower mobile phase flow rate. The slower the better. You'll actually see applications in literature of things like nanoflow and things like that. In reality, we need to use a higher mobile phase flow rate. So we have to do something called add that nebulizing gas. Remember that first slide with the yellow arrows of nebulizing gas? That's to help form those droplets. The use of volatile phases and the use of volatile buffers facilitates ionization because it facilitates droplet shrinking, which allows more ions access to the surface so they can pop off. Electrospray is concentration dependent. It is ionization is increased, or efficiency is increased by increasing the concentration of the analyte at the end of the capillary tip. Add the addition of matrix modifiers like the formic acid and ammonium formate matrix modifier helps form positive ions. It's like a pH 3 solution. So if put it just water and methanol, it might be pH 7. I'm going to get a lot more ions form from something that wants to add that positive proton on there if I put it in a high proton-rich environment. And also, here's one other thing: is chromatography helps produce a narrow band of highly concentrated analyte. And the reason that's important, if you go back to let's see if I have another slide. Nope. Remember the droplet? When it's being formed, remember I told you it's enriched in the ions? It's enriched by whatever's coming off the end of that tip. And what you want there is a highly concentrated band of analyte and not just a blob of whatever. If you're bleeding your analyte real slow out, you're going to get droplets that have some analyte in it and have some other stuff in it. But if you have a highly concentrated band of analyte right there, because you've done good chromatography, then that droplet is going to be full of your analyte and less of other things. So getting your analyte away from other things, like the proteins that I want to don't want to be in there, is really important. And that's why I think chromatography is so important to MSMS, even though it's LC just because that's what the technique is, and everybody's talking about MSMS. What are the pros and cons of electrospray? It's really soft. You see very little decomposition of the analyte, or you can optimize the source so there's very little decomposition of the analyte. It generally produces only molecular ions, so we see a lot of N plus H, but very little of fragmentation if you set up the source right. Multiply charged analytes are easily produced, so you can easily analyze proteins if that's what you want to do. You can do a wide range of analytes. I haven't hit anything that doesn't work at all in it yet. And it produces ions very efficiently. And because its efficiency is so good, that means that you're going to get lots of sensitivity. In fact, you may see after you start doing casework with an LCMS that sensitivity is not your problem, it's oversensitivity. You need to kind of tamp it down a little bit. And you'll see plenty of that. Yeah?
In terms of efficiency, in terms of percentage, how much is the percentage of
I don't, that's a question I don't know the answer to.
And the other question is, since it is electrospray, most of the ions are formed in solution before they are nebulized. So in this sentence, are you referring to the ion production at the nebulizer or both the solution and the nebulizer?
I would say you could tune your solution to promote the ionization of one thing over another. What I'm talking about here is it's a good way to get ions out of the liquid phase and into the gas phase, into the mass spectrometer. So it produces more than enough sensitivity for you for most compounds that form stable ions in solution. It's a really good way to get those ions from one to the other. There are other methods that may not be as good. I found for us that it works very well, and what we're usually ending up with is too much, not too little. So that's really what I mean there. It's more getting them out of the solution phase and into the mass spectrometer. So with every good comes a bad. The cons are it uses a lower flow rate, so if you had just an LC stack and you're used to using a milliliter or 2 milliliters a minute, you're going to have to use less than that, probably less than a milliliter a minute. It is concentration dependent. It means you need to produce those narrow bands of analyte to be at the end of the capillary tip. It works best the lower the flow, the more efficient it is. And the analyte must form a solution phase ion. It's not going to really impart a charge very well if it doesn't form an ion in solution. And again, chloride salts and sodium salts are really good indicators of suitability. So you can just flip open your drug standard catalog of choice and start reading and finding the ones that have sodium salts and chloride salts, and those are the ones, check electrospray. But the big bad is ion suppression. And ion suppression is something you need to deal with, and the easiest way to deal with it for our purposes is good chromatography. Ion suppression is the boogeyman of electrospray. It often results from inefficient droplet formation. It can result from other things as well. If you are adding non-volatile salts or buffers, remember things that are non-volatile impede droplet shrinking. Because a droplet doesn't shrink as well, it doesn't produce ions as well. Non-volatile materials in your mobile phase or ion pairing materials, should be a comma right there, can result in decreased ion efficiency. And it's reported that higher molecular weight ions can suppress smaller analytes. So you can imagine a protein, which is very high molecular weight, is going to suppress the ion formation or the ion release of a very small molecule. And I think a lot of that has to do with the fact that a very large ion is, if it's blocking the surface and it's from the surface of this droplet that my ion is formed, whatever's in that droplet that's blocking my analyte from getting to the surface is reducing its ability to form a gas phase ion. And remember that whatever's coming off the capillary tip at that point and is in that droplet is going to start interacting in a way to affect ion efficiency. So suppose I have a compound, two compounds in there, and one's really big concentration-wise and one's really small. What gets to the surface is really almost statistical, right? So if I have 50 milligrams per liter of methadone and 1 milligram per liter, 2 micrograms per liter of something else, what do you think is going to be mostly at the surface? It's going to be the really concentrated sample. So as that droplet gets smaller, what's going to be popping off the surface? The highly concentrated compound. So again, separation of analytes is not unimportant. And it really does underscore, like I said, the need for good chromatography. And as an example, we did an experiment in our lab where we infused oxycodone into the instrument at a steady rate. And you can see that. Let's see, get to use the righty thing. So this is basically a baseline level of oxycodone being infused in the instrument. And at the same time, we injected a biological specimen. So this is a extracted negative blood sample. And you can see all of a sudden, for this time period right here, I lost 90% of my oxycodone signal, which is really fine if I'm infusing oxycodone, but it's not fine if I am testing for 10 micrograms per liter of oxycodone. Because if I lose 90% of 10, I'm left with something I can't see. This is why good chromatography is so important to electrospray. The keys to remember for electrospray: it's a soft technique producing molecular ions, so just start thinking about M+1. So your cocaine's 304, your methadone is 310, things like that. Drugs that form HCl salts will be analyzable in positive mode. Volatile buffers and mobile phases will increase ion formation and ion efficiency. Good chromatography produces concentrated bands of analyte at the nebulizer tip, which will increase ionization efficiency. And poor cleanup can lead to significant ion suppression, usually at the beginning of the LC run. So poor cleanup is whatever, really depends on your application. For us, we do one-step precipitation, and all the things all the biological junk mostly comes off at the beginning, and so everything else that comes off much later in the run, we're fine. But the things that come off at the beginning are not very visible to us. Okay, so we formed an ion. We got out of our liquid. We did some chromatography. We separated stuff. We formed a droplet by nebulizing it, just like a sprayer. We shrunk the droplet. We got an ion. So now we've sucked it in the mass spectrometer, and the question is, well, okay, so what kind of mass spectrometer, and what can I do with it once I've got it in there? And more appropriately, how are we applying that to the analysis? At first to postmortem specimens, but now traffic specimens as well. So tandem mass spectrometry is the heart of this lecture, or the heart of what you're going to be looking at. There are really two basic geometries. One is triple quadrupole, Q, and then the little q, and the large Q again. You'll see that sometimes the middle Q is for the collision cell. It's not a filtering collision cell. It's really just an ion pipe. So sometimes people put the little Q in there. But it's two mass filtering quadrupoles that bracket an RF only collision cell. And by RF only, that just means it passes ions from one into the other and doesn't separate ions at all. It just says Whatever comes in here, I'm spitting out over there. That's what the collision cell is. Ion trap. The single really small ion trap serves as a mass analyzer and collision cell. So mass analysis and collision and fragmentation all occur in the same exact space, whereas in a triple quadrupole, they are separated in space. And hybrids, which is the type of instrument you're going to be able to use here, is an instrument. Our instrument, or the one you're going to be working on, is in the triple quadrupole geometry. That is, there is a filtering quadrupole, a collision cell, another filtering quadrupole, and the instrument here is the last quadrupole can also act as an ion trap. It's a linear ion trap, or LIT. And that quadrupole, it can either act as a quadrupole or it can trap and store ions like an ion trap. And can do a lot of the experiments an ion trap can do as well, with some advantages and some disadvantages. So triple quad versus ion trap. Triple quadrupoles are very sensitive, especially in sim mode. Why are they very sensitive? Because in sim mode, I can spend 100% of my duty cycle looking at one ion. And because I can spend 100% of my time looking at an ion, I get really great sensitivity for that one. Not for other things, but for that one ion, it's everything I see I record. That means they're great for quantitation. You don't miss anything. If I put it in sim mode, I monitor 2 or 3 ions. I'm gonna get very good quantitation because I'm gonna have a very fast duty cycle, and I'm never gonna be closed, which we'll talk about when we get to ion trap. And what I end up with is a lot of points across the peak, and the more points I have across my peak, the better I'm going to be for quantitation up to a point. And at some point, if I have 10,000 points, it doesn't really matter. But if I need to get 10 or 20 to get really good quantitation, triple quadrupoles are great for that. Triple quadrupoles also have some useful MS scanning modes. We'll talk a little bit about that, but the ones we're going to focus here on are AMRAM and product ion scanning, both of which a triple quadrupole can do. The limitation of a triple quadrupole, because it's not a mass storage instrument, they don't hold anything, they don't trap anything. I can't do MS-SCAN, which means I can't fragment, select another fragment, fragment that one, select another fragment, fragment that one, so forth and so on until I've taken my very large molecule and broken it down by successive repeated fragmentations. I can only do that in a storage instrument. So I have to do that in an ion trap. I cannot do that in a triple quadrupole. The other limitation is that they cost more than I do. They're very expensive because they're very large. They have lots of fancy quadrupoles that are gold-plated. And so, you know, in the sense that I can either get it or don't get it, expense is actually a real limitation, especially to a government laboratory. They're generally limited to lower resolutions. Unit resolution is pretty common. I think the resolution really depends on the length of the quadrupole, which again, longer quadrupoles, better resolution, more money. For our purposes, we sort of limit ourselves to unit resolution, so I can tell the difference between 303 and 304, but not maybe 303.001 and 303.002. They are less sensitive in full scan mode. As you're aware of, in single quadrupole, you know, only one ion gets from one end to the quadrupole to the other at any particular moment, which means that every other ion I form from fragmentation is lost, which means in order for me to get a really sensitive full scan mass spec, what do I have to do? Keep scanning over and over and over, adding my scans up until I get a full until I get a really great mass spectra. Okay, that's great. If I'm infusing something at a constant rate, I can just spin as long as I want. But if I'm looking at a peak, I only have this long until the peak is gone, 30 seconds or something like that. And so, because of that limitation, they sort of are less sensitive in full scan mode. In other words, because I'm not trapping, I'm losing everything, so I get what I get. If it's a really intense peak, I get a great spectra. If it's a really small peak, I get a spectra. Whether I can match to it or not, I don't know. The advantages of an ion trap instrument is they are really great for full scan sensitivity. Why? Because everything I put in there, I trap and hold, and then I fragment, and I keep and hold all my fragments, and then I can scan them out one at a time in an ion trap instrument. That means I'm really sensitive for full scan because everything I form fragment-wise, I can get at the detector. They have higher mass resolution because mass resolution in ion trap is controlled by how fast I scan it out of the trap. So if I scan very slowly, I get great mass resolution. If I scan very fast, I get lower mass resolution. And because it's an ion storage instrument, I can select a molecule, 304 for cocaine, fragment it, get to 182, trap that one, just 182, and fragment it. Trap whatever its products are, fragment those, and keep on going until I'm down to the whatever's the stuff that's too small to care about. So I can do MS, 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 MS in an ion trap. The limitations, they're not so good for quantitation. Why are they not as good for quantitation? Because they have a duty cycle. Ion traps have to open, fill, close, scan, empty, open, fill, close, scan, which means that for the period of time when the instrument is closed, all that information is being lost. Everything that's coming off the column is not going into the mass spectrometer because it's closed and doing what it's got to do. Ion traps also have something called space charge effect. The way I understand space charge effects, essentially the ions begin to sense each other's presence because the trap is so full of ions, and it causes mass defects. That's not a problem with quadrupole because only the ions are isolated from each other, and only one at a time hits the mass spectrometer, hits the detector. In an ion trap, the trap fills with charges, and if it fills with too many charges, then they can actually affect each other. Ion traps are also affected by something called the 1/3 cutoff rule. So, suppose I want to fragment cocaine, which is 304. The 1/3 cutoff rule says when I isolate 304 and then begin to fragment it, ions that are too far away in mass from that 304 become so unstable that I lose them. They actually collide with the sides of the mass spectrometer. So the 1/3 cutoff rule for ion traps is if I select 304 to fragment, really anything below 100 I'm going to have very low sensitivity for. And that's a limitation of the ion trap. So if you're looking for cocaine and you want to see that 82 ion, you're not going to see it very well with an ion trap. And they cannot perform some MS experiments that a triple quadrupole can perform, but they can do product ion scanning and they can do MRM. So here is the triple quadrupole configuration. Let me see if I can use the fancy pen again. This is the configuration of the instrument you're going to be using as well. This Q0 here is a focusing quadrupole. It's really designed to get things sort of settled down after they come in from the source, because they have all kinds of wild trajectories and energies when they come in from the source. And they need to be focused onto the first quadrupole, which is Q1. Q1 is the scanning quadrupole. It's an RFDC quadrupole. Q1 and Q3 are mass filters. That means they can select masses. They can sequentially scan masses 50 to 500. 50 to 550 is pretty much what we use in the laboratory. Or actually we do 40 to 550, I think. And they can also be used to select a single mass. So I can separate 304 from all other masses. And that's a lot of what Q1 spends its time doing. Q1 spends a lot of time selecting a mass from all other masses in order to fragment only that mass in Q2. Q2 is an RF-only quadrupole that's filled with gas. It's actually got a very low pressure of gas. I think 3 times 10 to the minus 5 torr of in our case, nitrogen gas. It is the collision cell, and this is where we want fragmentation to occur. So if I select 304 here, I want to put it in here and fragment it to a lot of different fragments, and then I want to look for either all the little fragments in here or just the one fragment, depending on what my application here is. Q2 does not filter ions. In other words, it doesn't separate any, whatever fragments formed in there get pushed out to the third quadrupole, which is another scanning quadrupole. It accepts all ions sent to it by Q1 and passes all ions formed inside of it to be sorted by Q3. Does that make sense? So far, so good? All right. They tell me I have to press this one. Triple quads in scanning mode, 99% of all ions are lost between the rods, so that means they have poor full scan sensitivity. In sim mode, 100% of the selected ion reaches the detector, which makes them highly sensitive and great for quantitation. The mass resolution is typically limited to unit, which I'm going to talk about here is basically plus or minus 0.2 AMU. I think what you define as unit may depend on what your manufacturer is. When I say unit, I mean plus or minus 0.2 AMU. Fragmentation is controlled by the energy ions have when they enter the collision cell. The higher that energy or collision energy, the greater the fragmentation. So if you really want to blow something apart, give it lots of collision energy, and congratulations, you'll form lots of tiny ions. All right, and you'll see what I mean by tiny ions when we get to that part. The collision cell on the instrument we're going to use here, it's called a LINAC. This is a linear accelerator. It's filled with nitrogen gas at about 3 × 10⁻⁵ torr. It drives ions out and reduces crosstalk. What do I mean by drives ions out and reduces crosstalk? You know, my Q1 selecting an ion and it's getting pushed in there and all those fragments are being formed. Well, I need to get those out and into the Q3 and sorted before I enter the next one in. So when I go to 310 to look at methadone, I don't want any of my cocaine stuff left in there. So the LINAC helps to accelerate those ions out, clear it, so that I can send the next thing in. It does that very fast. If you don't do that, if it didn't do that very well, then I would have a hard time telling the difference between things that were entering the collision cell in sequence. The analyte molecules undergoes collision-activated dissociation, CAD. And that dissociation is caused by the energetic collision with the nitrogen molecules within the collision cell itself. The nitrogen inside also acts to cool the fragments, facilitating their transport to the detector. It took me a while to figure that part out. Essentially, I take my molecule in there and I blow it apart by activated collision with the nitrogen molecule. So now I've got this exploded molecule and I've got fragments flying everywhere, right? I got to get them back in focused towards the exit lens, and that nitrogen helps to do that. So it both causes the fragmentation, but also helps cool, so take some of the energy away from those fragments so that they get pushed back towards the exit lens. Does that make sense? Alrighty. All right, so ion traps. I'm always forever trying to find a good way to draw an ion trap so that it makes sense. You can see that I have failed again. But the way I want you to think about here at the top, wait, I've got the pen. At the top here, at the bottom, that's just a ring electrode that goes all the way around, and there are two cap electrodes on either way, on either side, and basically ions come in and fill the space between the end electrode and the two cap electrodes, and that space is filled with a low pressure of helium gas. So the ions come in, they get cooled. Cooled means they have all this energy, and now they have less, and they just cycle around there until you decide to do experiments with them, like select one to fragment or scan them out, depending on what your experiment is. Mass analysis and fragmentation occur in the same space, and that's the important thing to remember about a trap. That's why it has to go through a cycle, where it closes, does an experiment, and then opens again. In full scan mode, ions are filled and are trapped in space, and the masses are scanned out of the trap sequentially. Ions are not lost, so full scan sensitivity is even better. So whatever fragment ions might enter the trap, they would have been fragmented in the source. Whatever ions enter the trap, once the trap closes, all those ions can be scanned out so you don't lose anything, so you have fuller scan sensitivity. What you're losing at that moment is whatever's coming onto the source at that moment. That trapping and filling cycle is what makes them poorer at quantitation. Mass resolution is controlled by speed at which the masses are scanned out of the trap, so slower scanning means better resolution. Tomorrow I will show you an example of that. In MS mode, ions are trapped. Fragmentation occurs when the selected ion is excited by something called a tickle voltage. Lord knows I don't know what a tickle voltage is. I probably would have to fill out some special forms of the GBI if I talk too much about tickle voltages. It collides. Basically, the ion collides with the bath gas that's filling the space already. So I tune my voltage to excite one particular ion, fragment it by collision with that bath gas, and then I can select another one and fragment, and select another one, fragment, and that's why I can get that MS, I think 16 or 20 times or whatever is the record. I don't know how you would do that with a small molecule, but whatever.